antiparticle, its sort of mirror image called an antiproton. All these quarks have got antiparticles called antiquarks. Complicated, isn't it? So a pion, in fact, has just got two quarks in it, but one of them is an antiquark. Okay? If you want a good introduction to all this, can I recommend this website, The Particle Adventure? Intended and aimed for kids, which means that some adults might be able to follow it. It is very down to earth, very simple, but actually very authoritative, so strongly recommended. I shouldn't really have put this next particle data group thing in, but if you think that this standard model is complicated, look at that website. That is a technical website of all the information. It summarizes all the information that is known about all the particles. It goes on forever, and you will see that actually the standard model is incredibly simple, because it summarizes thousands and thousands of other particles that have been seen, and it agrees with all of them. I'm quite happy to email stuff to you about this. Here's my email address, paul@wraight.net. But I'd recommend the top one, the middle one with my tongue in my cheek, because it's incredibly complicated. But it gives you an idea of how complex this is, and what a wonderful simplification the standard model actually is. For how the Large Hadron Collider works, there's a very, very good film on YouTube. So it's called LHCb, The Beauty Experiment. If you look at that one on YouTube, it's about 15 minutes. It's a very, very good picture of one of the experiments and how it works. Strongly recommend that. Okay, now 3 comments on this standard model. First of all, it is incredibly successful in the thing that matters in science. It agrees with experiment. It seems to agree with every experiment. Very hard to find anything that doesn't agree with it. But it's got a whole series of arbitrary numbers in it, which it just put in to fit. In other words, the mass of the quarks, or the strength of the forces. There are numbers which are put into the theory in order to make it fit the experiments. And these 20 numbers fit thousands of experiments, so it's jolly good. But where do they come from? Nobody knows. They're just numbers that are put in to fit. And thirdly, it leaves some very basic questions unanswered. There are 3 sets of particles, you know, up-down quarks, strange and charm, top and bottom. Why 3 families? Nobody knows. Unanswered question. We think the Higgs boson exists. Not quite sure, there's beginning evidence for it, but the theory doesn't say what its mass is. What it does is, if the mass is so much, then we can work things out, but we don't know what the mass is. Okay? Neutrinos seem to have mass, but we have no idea why, and not really how much. We do know that they change into each other. And are these 3 forces related to each other? Well, the standard model sort of relates the electrical and the weak force, but it doesn't relate them to the strong force, and certainly doesn't relate it to gravity. So a series of quite serious basic questions which are not answered by the standard model. So almost nobody thinks the standard model is the final theory of physics, even though it agrees with every experiment. A bit more about this. Here are these 4 forces: gravity, the strong nuclear force, the weak nuclear force, and the electromagnetic or electrical force. Well, in the experiments that are being done at LHC, we're trying to find out about the way in which electrical and weak forces are tied up together by the Higgs boson, in fact. They probably are tied up. If all those 3 forces are tied together, that's what's called a theory of grand unification, and no successful such theory has yet been produced. And if you try and put gravity in as well, well, no one's done that either. Those string theory is an attempt to do that. So, the standard model, very successful, but nobody thinks it's the final theory, and we'll come back to some of these things in talk 3. Now, let's say a wee bit about the Higgs boson, because you've probably heard about it. It seems to be an essential part of the mathematical structure of the standard model. In other words, take the Higgs boson out and how does it work? You know, big problem. So it seems necessary. It explains why some particles have mass and other particles don't have mass. And in fact, it's the one part of the standard model that hasn't yet been found, although maybe it has been found now, we're still not quite sure. and looking for it was why they built the LHC. But if it does exist, it raises a whole series of serious problems. Like, there's this Higgs field. Why does it have gravity? It ought to have a huge amount of gravity, and nobody knows why. So big problems. And neutrinos are another problem. Neutrinos are produced in radioactivity. They're produced in nuclear reactions. For example, in the middle of the sun, huge numbers of neutrinos are produced every second. But neutrinos are odd in that they fly right through everything without hitting anything. They will fly right through the sun without hitting the sun. They will fly right through the Earth, and 99.9999999% of the time they don't hit anything. Very hard to catch. They have almost no mass. They hardly interact at all. And there are 3 kinds of them, which actually explains, is the solution to what was called the solar neutrino problem. People had this model of how the sun works, the nuclear reactions which actually drive the energy of the sun. And they predicted the number of neutrinos that would be produced. And in an experiment for many, many years, they measured these neutrinos and only got about 1/3 as many as they expected. And people couldn't work out why. We now know why. There's 3 kinds of neutrinos, and they actually change into each other as they travel. So if you start off with one sort, you finish up with all 3 sorts. If you only measure one sort, you only get 1/3 of what you expect. Understand? So it's a lot is being discovered about neutrinos. You may have heard that people have thought they measured them going faster than light. This is what they did. It's part of the LHC, and the super proton synchrotron, zooming particles around, is actually able to produce a neutrino beam. A beam of muon neutrinos, which travels 700 kilometers under the Earth and can be detected down in Italy there. And what they're actually trying to do is find out whether these mu neutrinos turn into Tor neutrinos. That was the point of the experiment. And blow me, when they did the experiment, they seemed to find that they were travelling faster than light, a little bit. Huge mystery. Almost nobody believes it. It raises so many questions if it's true. But as far as I know, no one's solved the mystery yet. So I don't believe they travel faster than light, but that's where they are. Now, that was all by way of introduction. The main point of this evening is as follows. There are these remarkable coincidences about the constants and the laws of physics, which are essential for life, but we have no explanation for them. They seem to be random coincidences. First example, the mass of the neutron. I said neutrons and protons about the same mass, about the same weight. But actually the neutron is just a little bit heavier. And it can decay. It's got enough energy, enough mass, that in about 10 minutes it decays into a proton, an electron, and a neutrino. Okay? It's got just enough energy to do that. In fact, if the neutrino had 1% less mass than it has, it would be lighter than the proton. And then the opposite would happen. The proton would decay by radioactive decay into a neutron. Okay? So it's just a question of which is heavier that determines which one decays. Now, if the proton were unstable, that would be absolutely disastrous. Because hydrogen would be unstable, nothing would be stable, there wouldn't be any matter in the universe. Because hydrogen and all the other elements would just decay radioactively, and there'd be nothing, except neutrinos and photons and things. So it's absolutely vital that the neutron is a bit heavier than the proton. But it's also vital that it's not too much heavier. If it was another 1% heavier, I said neutrons decay in about 10 minutes, but inside a nucleus they're stable. But if it was a bit heavier still, then it wouldn't be stable even inside a nucleus, and then again everything would fall apart. Nothing would be stable, there'd be no matter. So it's absolutely vital that it's just a bit heavier, but not too much heavier. So, the question is, well, what determines the mass of a neutron? Well, remember, neutrons and protons are made of quarks, 3 quarks each. Neutron is up, down, down, and a proton is up, up, down. So the neutron is a bit heavier because D is a bit heavier than U. Okay? And what's that? Let me show you a diagram. Here is a diagram of the masses of various particles, and concentrate on the quarks, the down quark, the up quark, the strange quark, the charm quark, the bottom quark, and the top quark. The ones in red are the ones with plus 2/3, and the ones in blue are the ones with minus 1/3, okay? They come in families. And blow me, the down quark is a bit heavier than the up quark, but the other ones are all the opposite way around. The strange one is lower and the bottom one's lower. So why is the down quark, it's absolutely vital that the down quark is slightly heavier than the up quark, because otherwise everything would fall apart, right? And it's also vital it's not too much heavier, otherwise everything would fall apart. Nobody knows. The Standard Model has no explanation at all of these masses. They just put in to fix it. Okay? There is no theory that says this is why quarks have this mass. It is purely a number. But it is absolutely vital to life. And if it wasn't pretty well like that, we wouldn't be here to think about it. Another example, a particle called the deuteron. You may have heard of heavy hydrogen. Deuterium, which is hydrogen with a mass of 2. It's got 1 proton and 1 neutron in its nucleus, and it's stable. And of course, it's the strong force that binds the proton and the neutron together. Now, when you do the sums, you find that the strong force is only just strong enough to make the deuteron stable. If it was a bit weaker, 20% weaker maybe, it'd fall apart. And if the deuteron fell apart, all sorts of things wouldn't happen. The whole theory of element formation in the stars and in the Big Bang depends on the deuteron as a vital intermediate stage. If deuterons were not stable, elements would not be produced, there wouldn't be anything worth talking about except hydrogen. Okay? But interestingly, if it was a bit stronger than it is, then 2 protons would be bound together. Currently, there's no such thing as helium-2. There's helium-3 and helium-4, but not helium-2. Just 2 protons. And if helium-2 did exist, then again, the theory said it would be a disaster. All the hydrogen would become helium and that would be the end of things. So it's quite vital that the strong force is just strong enough to make a deuteron stable, but not strong enough to make a diproton, 2 protons, stable. And again, the strength of the strong force is just a number in the theory. There's no explanation of how strong it is, you just put in the number to fit the numbers. Here these particles are going to do this thing again. You see that there's helium-3, but there's no helium-2. Okay? And that's very important. So, second example. Third example, and in some ways this is the most dramatic of all, so-called carbon resonance. We now are pretty sure that all the elements bigger, heavier than hydrogen and helium are actually formed by nuclear